Indirect load works like this. The instruction you use is LDI, load indirect, opcode 10. Yeah. And then you've got your destination register, and you've got a PC offset. Okay, now if you look at that, it is absolutely identical to the load instruction. Load, except that it has a different opcode. Okay. It looks identical. This is the only place that it differs. Now, in terms of action, this is what happens. It begins just like this one would begin. That is, it takes the contents of the program counter, which is the next instruction, adds this offset to it, gets you down to some location in memory. With this instruction, that location is the operand. That's what gets loaded into the destination register. With the load indirect, it takes the contents of that memory location and puts it in the memory address register and fetches something out of that location. That allows you to get anywhere in memory, because you can store a full 16-bit address in that memory location, and then by using the load indirect, boom, you can go anywhere. Because remember, one of the things about this is that there's a limit as to how far away you can actually look to find things to bring them into memory, or bring them into the registers. With the load indirect, there's no limit. But it takes an additional step. It's a slower instruction because it requires 2 memory cycles. You have to take the offset, add it to the PC, go to memory, fetch the contents of that location, but then instead of putting that into the destination register, you put it in the memory address register, and it goes out to another location in memory. For example,
Did you
let's
put
see.
those steps,
What?
the steps that it goes through?
Yeah, let's go through them here. Let's, suppose that we're at 3010 and we've got a load indirect. Well, let's see. 1010, which translates to a load indirect. And, okay, we'll go into register 4. And, let's see. I'll just make up a number here. Here's my offset. Just as a note there, it's 6. So, since the address of the next instruction is 3011, where it's going to go actually is 3017. That's where this instruction is going to look. Okay, we'll just write something here in text. We'll reach a long ways away. 468F. Suppose that's what's in that memory location. Then down here someplace way down along the line at memory location 468F, we have 0024. Okay, what actually gets put into register 4? This thing. Because the steps it goes through, here's the way it works. It actually does a sign extend on the, on this thing, gives out 16 bits. It adds the program counter, which is 30010001, and I get 00010111, which is 3017. Okay, so now it fetches the contents of 3017. Now, because of the indirect, this is what indirect means. We're not going directly to our operand. We're getting a step in between. That value, which is 468F, is used as a memory address for the actual operand. Okay, in terms of C, C++ kinds of constructs, what are we talking about? It's a pointer. This thing is a variable that is pointing to another memory location. That's really what's going on. The contents of this thing is not treated as an operand, it's treated as an address. So you don't go directly to your operands, you go indirectly through an intermediate step. And again, the real benefit of it is that with this offset, you can only reach so far. If you get a really long program, you've got problems at the beginning trying to get to your data, which is at the end, if you're more than you can reach in 9 bits. But by using this scheme, you can go anywhere.
So you would insert that value in 3017, that you would know that that memory address is what you want, right?
Yeah.
So you'd
Yeah.
have to insert.
You have to build it that
You
way.
have to build it that
Yeah, exactly. And, you know, like I say, if you've got a really long program that you can't reach to the data you want, you may have to insert a data statement, this thing, in the middle of your program somewhere, and then branch around it so that it doesn't get executed as code. Because you can get some rather bizarre results if you try and execute data as an instruction. Okay, that's the other addressing mode. We have now covered them all, so we'll now start getting a little more serious about writing some extensive code on these things. Yes?
So just with this branch, like the indirect, how does it know if it's pointing to something else or if it's actually a code? Like it's actually a branch?
What do you mean?
Like, cause it's getting the number there, the 4685.
Here? Mhm.
Yeah, how does it know it's going for another one? Like at what point does it know it's?
The key word is context. What's happening when that value is loaded into the CPU?
But how does it know which value to load? Like is it pointing to one, can it point to another one or can it only skip one?
Oh, you can only go one level.
Okay.
Yeah. And there is nothing magic about that number that says it's an address or actual data or an instruction. There's nothing magic about those bits. It's all about what is the processor doing when those things, when that's loaded in. If you're doing this kind of an instruction up here, because of the opcode, it knows that going to that location, it's going to contain an address. If you just change that to a 0, then it knows that when it goes to this thing, that's the operand. That's how it knows. I mean, there's nothing attached to a particular memory location that says, oh, this is an address. This is data. This is an instruction. Doesn't work. There have been some architectures in the past that have done that. That is that on any given memory location, in addition to the however many bits there were in the thing, there would be a tag field outside of that of a certain number of bits that would identify that location as being instruction, data, data of different types, floating point, integer, whatever. Those kinds of schemes have not been particularly successful. They're too slow. It's too long for the system to sort through it. It's better if it's just done by context. Okay? Now, I think we've probably hashed programming in binary adequately. And so at this point, we'll start actually writing in assembly. Now, one of the things to recognize about writing in assembly, well, there are two things to note. Principally, one assembly language instruction corresponds to one machine code instruction. So, as we make this shift, it doesn't really shorten anything that you're doing. They're going to be just the same number of instructions. The advantage that we have, first advantage is it's easier to read. That is, add is easier than saying this. Okay. If you have to memorize all those opcodes and write them in binary way, it gets to be a real nuisance. But when we get these mnemonics for each of the instructions, it's actually easier to read and saves a lot of time and effort in working with it. So that's point number one. Two, the assembler will actually do some work for you. For example, it will figure the offsets. Beneficial, right?
Yes, love that in school. This is
Yeah.
how you do this. Oh, wait.
It does some other things too, but that's one of the principal benefits that it has, is that it will figure all those offsets. It will not, however, set up indirect addressing for you. You'll still have to do some fussing with that one yourself. Okay, so let's see. Let's see if we can write a little program here using the Okay. I'm looking at problem 6.2 on page 172. It doesn't say to write code to do this, but it says we want to subtract two numbers without a subtract instruction. Okay, we've done this, but we did it in binary. So let's see how we might write this thing up in assembly. I'm going to, what the problem actually asks you to do is to break this down. The typical problem-solving technique is divide and conquer. You put this down into separate steps. Okay, the steps that I would use would be, let's see, I'm going to figure x minus y. Okay, I will load y, find its negative, load the x, add, and store the result. Okay, that's the way I'm going to do it. Okay, so as I start to write this thing in assembler, remember the first thing you had to write in binary, that first line you wrote in binary was going to give you the starting address of where the thing was going to fit. When you start writing in assembly, it's done this way. You specify the origin of your program. It has become almost universal practice, not just on this machine, but on most of them. Any instruction that begins with that period is what we call an assembly directive. It tells the assembler to do something for you. It's not something that's executed when you get down to execution time. It's something that the assembler itself does. And when you get through all of this, why in the actual executable code, that's not there. Because it's the assembler that takes care of it. Okay, so my first step in my algorithm is to load y. Where am I going to put it? Well, let's see. Register mode is done this way. Let's see. And let's see, I was going to call it y. Okay. So I say load register 1 y. Now the thing to recognize here is that the addressing mode that's going to be used there is PC relative. Now you don't specify that. It just comes out by the fact that I have used what's going to end up being a label. Someplace down here I'm going to have a memory location that I'm going to identify as being y. Find its negative. Let's see. If you look back there, in the back, the negative, the first step in the negative is to do a not, which just flips these things around. Changes all the ones to zeros and all the zeros to ones. And then I add one onto it. that identifies that as being, to go back to our addressing modes, as being a literal or immediate mode. If you just put a 1 out there, it will see it as being typically a memory address. The pound sign there says this is a literal constant. This is the actual number that I want you to add. Okay, so we loaded Y. We have now, at this point, found it's negative. So now I need to fetch X. So I will load register 2 from X. So that's easy. Add them? Yeah, that's pretty easy. I'm just getting really uneasy about that.
It's on page 526.
Maybe that's what I want. Yeah. Yeah. Okay. The actual breakdown of the 3 operands in an add instruction are destination, source, and either second source or the immediate operand. But this is where the result is going to go. In some logical ways of thinking about things, that's kind of backwards. That is, some people would like to say, oh, this says add this to this and put it here. And there are some assembly languages that work that way. That's why I always have to double check myself and be sure I'm writing these things down correctly. Yeah, this one works. Add the last 2 together and put it in the first one.
That doesn't seem all that backwards.
Depends on your background and how you've worked with it, yeah. Note here the addressing modes that we're working with. This is PC relative. This one is immediate. And of course, this is, we've used these all the way through, but that's register mode. Haven't worked with either of the other 2 at this point. We'll do those later on. Add. Okay, now we just have to store the result, which is in register 1. So we'll store register 1 to result. That's all of our program, so we'll say halt. And now we can put in our data. Data works in kind of an interesting way. If I can refer you to I'm sure that there was it wasn't in chapter 6, but I thought it was. Okay. Typically, these things are set up with a margin here so that you indent there. Memory locations, you put your label that you're going to be working with, then a tab, and here's the assembly directive. We say dot fill. And then we put the value out there that we want to have filled into that memory location. And you can put it in hex. We would do y dot fill. Line, and then we had result. I would fill that initially with 0. 0 doesn't matter whether you're doing it in hex or decimal or whatever, it's all the same value. Okay, this is how you set up your memory locations. Get them so that with initial data or some initial value that you want it to start with. Okay, now you can go through and by hand translate all these things into a machine code program. It's not hard, a little time consuming, but it's a pretty systematic procedure. But this is what a program for the LC3 in assembler would look like. The way you would build the thing. The indentation isn't necessary, but it sure helps reading it. If you think reading somebody else's C++ code is hard, you ought to try reading somebody else's assembly language code. I have a brother that spent, I don't know how many years, enough that he retired from them, as a programmer with Bell Labs. Later, under various other names, with the big breakup of Ma Bell. He told me that one time he got a call from another computer expert in another one of the divisions. And he says, "Olson?" "Yeah." He said, "I understand you wrote the assembly code for such and such a routine." My brother says, when you get a question like that, you begin to think, oh, what did I do wrong? And he says, "Well, yes, I did." The guy says, "I want to thank you." He says, "You write the clearest assembly code I have ever encountered." It's a real job to read somebody's assembly language code. So anything you can do to help. One of them is to indent the instructions, not the labels. It tells the difference between a label, because we'll put labels up here on instructions too, so that we can loop and do things like that. It tells the difference between the label and the beginning of the instruction by white space, usually a tab character. That signals to the assembler as it's going through and trying to do all this translation into binary. That's the signal that this is the end of the label, and this is the beginning of the instruction. Yeah?
What's the typical number of spaces in a tab? 8?
8.
So your labels will probably need to be pretty short then.
Typically, they're pretty short.
Okay.
Yeah. They don't have to be. I mean, you could put in a 10 or 15 character thing and then a tab. But then if you want your instructions to line up and be readable, you want to double tab all the ones without labels. But yeah, typically at this level, we keep the labels pretty short. Tend to violate one of those make your code readable instructions
Right.
in high-level languages that say use meaningful labels and things like that. We do try to make them as meaningful as we can. I use result down there instead of just R. But, again, you do the best you can, but there are a few more constraints here than there are in high-level languages. Okay. This is really now where we begin. There is a nice discussion at the beginning of chapter 6, if you haven't read it, on problem solving, especially that first part on systematic decomposition. The real way to do any of these things at this level is to decompose the problem. And sometimes you have to take 2 or 3 stages of that to get it down to the level that you can work with it here. But one of the suggestions that I have made to people in attempting to write assembly language code, write it first in C or COBOL or whatever, high-level language, so that you can get yourself fixed on the logic of the thing and what are the steps that are going to go through. And then go through and figure out, okay, how would I translate this instruction? How would I accomplish that result in assembly language? That's the idea. So the whole approach to problem solving is to break it down into steps, maybe big steps at the beginning, and then look at each one of those and say, well, can I break that down farther? Until you can get a fine enough decomposition of the problem that you can write it out in the limited instruction set that we have. So that's the thing to look for and the thing to think about in terms of your next assignment, which I will give you on Wednesday. And at some point, we've got to talk about an example, don't we?